Welcome back, everybody. Today I'm going to continue to talk about support vector machines, also known as SVMs. The last lecture I taught you about what are called hard margin SVMs, or maximum margin classifiers. Today I'm going to talk about a more useful version called soft margin SVMs. And soft margin machines solve two of the problems that are brought up by hard margin machines. The first problem is that hard margin support vector machines, like perceptrons, fail if the data is not linearly separable. That's a pretty big limitation, because most real-world data sets are not linearly separable either. Now, there's a second problem with hard margin SVMs, which is more subtle, but is worth illustrating, which is that they tend to be very sensitive to outliers. And what do I mean by that? Let me show you an example from one of your textbooks. This is from Introduction to Statistical Learning. And what this example shows us, on the left, we've got a set of points and red points, and the support vector machine, the maximum margin classifier specifically, that separates those two. So that's what we got on the left. Now, over on the right, what's happened is that we have added exactly one new point there. Otherwise, the data set's exactly the same, just one point has been added. And when you add that point and solve again, you get a very different decision boundary, the solid black line here, than what you got before, which was the dashed line here. So just adding one data point, even possibly to a problem with a lot of data points, might cause a big change in the classifier. So it's very sensitive to a single point. This could be a good thing if you know that all of your data is extremely reliable, but sometimes a lot of real-world data has outliers, points that are just wrong, and you don't want a classifier to be this sensitive to one wrong point. Well, you don't want it to be sensitive to one point because you don't know which points are wrong. So we'd like something a little less sensitive than that, and soft margin support vector machines will help to fix that problem as well. So to solve those two problems, here is the new idea. Since we can't have always linearly separable points, we're going to allow some points to violate the margin. And the way we implement that is that we introduce to our optimization problem something called slack variables. And these slack variables are going to appear in our constraints. We're going to modify our constraints a little bit to add slack variables. And here's how we modify the constraint. Specifically for training point I, formula, this is the spotty. Let me quickly see if the other one is better. Try changing out microphones. I hope this one's better behaved. Seems to be ringing less anyway. All right. Here's the modified constraint, again, for point I. So this constraint here is almost the same as the constraint that we used for hard margin support vector machines. But there's this one addition at the end here, which is the slack variable. That's the Greek letter xi. So xi subscript I is a scalar slack variable for sample point, training point I. We're also going to impose some new constraints in addition to the ones we were imposing before, that say that the slack variables are never negative. So we also need, for each sample point I, we need the constraint that its slack variable, xi subscript I, is always greater than or equal to 0. So what this inequality does is that it ensures that all of the sample points that don't violate the margin are treated the same. They all have xi I equals 0 in the optimal solution. A point I is going to have a non-zero xi I if and only if it violates the margin. So what does it mean to violate the margin? Let me show you a few examples. All right, here's a picture of the margin found by a soft margin support vector machine for a particular set of points. So you can see the blue C's are in class C and the red X's are not in class C. And a few features to notice about this figure. First of all, the big black line in the middle is the decision boundary found by the soft margin SVM. Second, you will see this slab here. there's the slab just like we had for a hard margin support vector machine. But something very important has changed. We are actually changing the definition of the word margin. So just as before, just like with a hard margin support vector machine, the soft margin machine will have a margin equal to 1 over the length of the vector W that is in the optimal solution of the problem. And so that margin is on both sides of the decision boundary. And so you get this gold slab I've drawn has a width of 2 over the length of W. But remember that last week the word margin was defined to be the distance from the decision boundary to the nearest sample point. Well, when you have linearly separable points, that definition makes sense. But when you don't, that definition is kind of useless. The distance between the decision boundary and the nearest point should be 0, and sometimes should be 0. So we are keeping the definition of margin that says it's 1 over the length of the weight vector W that optimizes the optimization problem that we're about to study. But the original definition of margin, distance to the nearest point, forget that. That does not apply to soft margin SVMs. Instead, what happens is you will see that there are some points that violate the margin. Well, first of all, what are the points that don't violate the margin? Well, all these red X's here are cool, and all these blue C's here are cool. They don't violate the margin. So there are two different ways that you can violate the margin. One way is you can be inside the slab. So if you have a point that's inside that gold-colored region, that is violating the margin. But there's another way you can violate the margin, too. If you look at this red X here, it's not inside the slab, but it's completely on the wrong side of the decision boundary. That X is where the C's are supposed to be. So those are two examples of points that violate the slab, as do this one, and this one. So those are the 5 points that violate the margin. Those are the 5 points for which xi will be strictly greater than 0. And how much greater they are than 0 actually tells you how far they violate the slab. Specifically, you'll notice that I have tagged this little arrow here that shows how far the X penetrates into the slab with a distance of xi1 over the length of W. So that's the actual distance of the actual length of that arrow there. And likewise for this class C training point here, it violates the margin by xi5 over, sorry, I'm getting them mixed up, xi4 over W. So what the slack variables tell you, again, is how far does a point violate the margin? How far does it enter into that gold slab, maybe even come to the other side? And so for most of the points, they're not going to violate the margin. And so again, these points will have xi equal to 0, and so will these points. So let me just reiterate that we are redefining the word margin when we use soft margin support vector machines. It just isn't the distance to the nearest, from the decision boundary to the nearest training point anymore. It is now 1 over the length of W, which is completely consistent with hard margin support vector machines. Now, with this formulation in mind, we're allowing variables to have some slack, but we don't want them to use more slack than necessary in some sort of kind of way, for some sort of kind of definition of necessary. We want to prevent slack from being abused. We want to allow a certain amount of slack, but we don't want to allow too much slack. And so the way that seems to work best to keep the slack from getting too large, to keep too many points from violating the margin, is that we add an extra loss term to the objective function, which is basically the sum of all the slacks. So we're not only trying to minimize the length of W, now we're trying to minimize the sum of all the slacks as well. And that's going to give us the following optimization problem. We want to find a weight vector W, a bias term alpha, and a bunch of slack variables xi I, one for each training point, that minimize the following objective function. Just like before, we're going to minimize the length of W, just like with a hard margin support vector machine. Minimizing the length of W maximizes the width of that margin, just like it did last Wednesday. And just like on Wednesday, we're going to square it, because it gives us a better behaved objective function, a smooth one. But we're also going to add all the slack terms. So there is some constant C times the sum of all n slack terms. That's our objective function. I'll say more about C in a second, but it's just a real number. And you played with it a lot in homework 1, so you're somewhat familiar with it. And this is subject to the following constraints. There are the constraints that we hope that most of our points are classified correctly and outside the slab. But because slack variables that do allow some points to be classified wrongly, which is good, because if your points are not linearly separable, you need that. And so there's one of these constraints for each sample point. And then we also require that the slack variables, again, are non-negative. All right, so that is our formal optimization problem. This is a, rigorously defined problem that we can think about what algorithms will solve that problem. And there's a name for this kind of problem. This is recognizable as something called a quadratic program, which is good because quadratic programs have been studied a lot. And it is in d plus n plus 1 dimensions and 2n constraints. The 2n constraint should be pretty obvious. We have two different kinds of constraints, each one for each sample point. The d plus n plus 1 dimensions, well, W is d-dimensional. The slack variables, there are n of those. And then there's a bias term alpha, which is the 1 in the dimensions. Now, when I say it's a quadratic program, what that means is that it has an objective function that is quadratic and positive semi-definite, with a positive semi-definite Hessian, and its constraints are linear inequalities. That's, if something is like that, we call it a quadratic program. So let's come back to this constant C now. So what's happening here is that the optimization function itself, the cost function, is juggling two different desires. On the one hand, we have the desire to make the margin as wide as possible, which we do by making W as short as possible, the vector W. On the other hand, we also have the desire to keep the slack variables small, so we don't have too many points that are violating the margin and perhaps being misclassified. when you have two different goals, you have to decide how you're going to trade them off. Which goal is more important to you? That's what C does. C essentially establishes the relative priority of these two goals. So if you make C bigger, that means you're really emphasizing the slack terms. If you make C small, you're more interested in maximizing the margin. C should always be set greater than 0. It doesn't ever make sense to use a negative C, because then you're rewarding slack. Now, C is a hyperparameter. It's sometimes called a regularization hyperparameter because it helps regularize the solution. I'm not going to tell you what that means today, but in about 3 weeks we'll talk a lot about what regularization is. For now, you just need to know what is the trade-off between choosing a large C versus a small c. Well, I'm going to make a little table where I'm going to compare for various metrics what happens if you choose C to be small versus what happens if you choose a big value of C. And so, first of all, what is the desire that we are satisfying? Well, if you choose a small c, it means that you're trying to maximize the margin, and you give higher priority to that over the slack terms. Whereas if you choose C to be big, that means you're prioritizing the slack terms, keeping most of them 0 or small. And so you can choose C anywhere in the middle to trade off these goals. Now, if you choose C too extreme in one direction, you won't get as good a classifier as if you choose the optimal C, which is usually somewhere in the middle. So what can go wrong? Well, if you choose C too small, you wind up underfitting. You're so interested in maximizing the margin that you're ignoring the slack variables, so you might wind up misclassifying a lot of the training data. And just have a low training accuracy. On the other hand, if you set C really big, then there's a very different danger, which is you might actually overfit the data. And as usual, the telltale sign that you've overfitted is that you might have training numbers, training accuracy that's much better than your test accuracy. Now remember, one of the things that I said motivates hard margin SVMs is outliers. What if you have points that are just wrong in your data set? How much do they affect the output of your soft margin support vector machine? Well, if C is small, then that has the nice property that it makes it less sensitive to outliers. No one training point has an unduly large influence on the decision boundary, which is usually a good thing, especially if your data is unreliable. If you make C big, then it becomes more sensitive, which is only a good thing if your training data is extremely reliable. I want to say something about what kind of boundaries you get when you use nonlinear features. So this won't make sense yet, but the second half of this lecture is going to be about features, how we can use linear classifiers to get non-linear decision boundaries. So suppose you're doing something that gives your linear classifier a nonlinear decision boundary. What you'll tend to find is that you make C small, you're more likely to get a flat decision boundary, or at least one that curves slowly, small curvature. Whereas if you choose C to be big, you tend to get more sinuous decision boundaries when you're using nonlinear decision boundaries. Obviously, a linear decision boundary can't be sinuous. It's perfectly flat. But these are the phenomena that we see when we go up to higher dimensional or higher order features, as we'll see later in this lecture. So now that we know these trade-offs between having a big C versus a small c, how do we actually choose C? Well, you already learned that in homework 1. In practice, the best way to choose it is to use validation. Ultimately, your data has to decide whether you want to be in the big C domain or in the small c domain. Yeah? Well, what scale am I working with? It really does depend on the scale of your data itself. So, if you scale your data by 100, C will typically scale by 100. So that's the first thing to keep in mind. Usually we do look at geometric series of C. C isn't in some small range, but we ask, what if C is 1,000th, 100th, 1/10th, 1, 10, 100, 1,000, etc.? Let me show you a figure that shows the trade-offs for various C's. So here are 4 different figures. So by the way, this figure is taken again from your main textbook, Introduction to Statistical Learning. And all 4 of these examples have exactly the same training set. So the data is not changing from picture to picture. What is changing is just the value of C. So the smallest C is at the upper left. And the largest C is at the lower right. And then, well, this is the smallest, then this is getting a little bigger, this is getting a little bigger, and this is the biggest. So what you can expect to see is that the bigger the margin is. So in the first diagram, you can see we have a pretty extreme margin. The margin is so wide that almost all of the training points violate that margin. And that is what will happen often if you choose C really small, is that it just doesn't care about violating because C is so small. Then, you make C a little bit bigger, and it starts to reduce the number of points that violate the margin. You make C a little bigger, and now most points don't violate the margin, but there are some that do. And for the biggest C of all, there's only a few points left that violate the margin. In this example, you can also see how the decision boundary is changing. It's kind of rotating in different ways depending on what you're trying to achieve here. So one way to think about slack is to pretend that slack is money that we can spend to buy permission for a sample point to violate the margin. So, this sample point here, we have to pay this much slack, the length of that arrow, to allow that blue point to live on the wrong side of the decision boundary. The further a point penetrates the margin, the bigger the fine you have to pay. We want to make the margin as wide as possible in principle, like at the upper left, but we also want to spend as little money as possible on violated margins. So there's this trade-off. If the regularization parameter is C is small, like at upper left, we're willing to have lots of violations. And you can see there's lots of violations of that margin. but we get a wider margin. If C is big, like at the lower right, it means we're cheap. We don't want to pay much for violations, even though we'll suffer a narrower margin. And let me add that in the extreme case where C goes to infinity, essentially what you're going to have is that your soft margin machine approaches behaving like a hard margin SVM. So think of the hard margin as being one extreme of the spectrum where you set C all the way to infinity. Yes?
So it seems like, well, the black line is the decision boundary that you have the diagonal line of the decision margin.
That's right.
What's the interpretation for data that's on the correct side of the decision boundary but within the margin?
What's the interpretation for data that's on the correct side of the decision boundary, but inside the margin? That is considered to be a violator. So, for example, this blue point here, that's on the correct side of the decision boundary. So it is going to be classified correctly, which is good, but it's still not as far away from the decision boundary as we want, so we're still paying a penalty for that. It's not as big a penalty as if it were misclassified, but we still pay a penalty.
Would that be like your uncertainty? So even though that's like classified correctly, you're kind of uncertain about the data.
Yeah, so describing it as uncertainty, I think that's a good insight, is that this really is related to the uncertainty of the classifier in some deep ways that I can't get into today. And so the wider the margin is, the more likely it is that your margin on your test data will be better, your margin on your training data, pardon me, will change better to your test data. Mm-hmm. Other questions? Yes? Is it possible to have powers instead of 2 over the norm of W? You could. I don't know if people have explored this much. I mean, there's no reason in principle why you couldn't replace the W squared with W to the 4th power. Did that would kind of differentiate how the algorithm treats small values of W versus big values of W. I'm not sure it would give you a very big difference. In fact, once you tune the hyperparameter C, it might make very little difference. But you could do that. I think that the fact that support vector machines have been used for decades, and people have settled on this particular objective function as being one of the most effective, I think that's a sign that squared is probably the right one to use there. But maybe there are applications where some way to modify this objective function might work better. Other questions? Mm-hmm. Larger C's mean that training takes longer. Yeah, that is a good observation, and that's actually related to the last thing I said, which is, in the limit as C gets really big, we're approaching a hard margin SVM. And you can see why that might be a problem if your data is not linearly separable. If you have data that can't be classified by a hard margin SVM, then the bigger you crank C, the harder your soft margin SVM has to work. Now, there's always a solution as long as C doesn't actually go to infinity, but in the limit as C goes to infinity, you're making the problem harder and harder. Other questions? Mm-hmm. Oh, are we going to talk about algorithms for solving this minimization problem? Not in this class. I would like to, but unfortunately, we just don't have enough time to go deep into optimization algorithms this semester. Mostly we'll study gradient descent a lot, but other optimization algorithms like quadratic programming, they're really interesting, but there just isn't enough time to fit them into this semester. I think that EECS 127 is a great starter course for learning more about optimization. And then, of course, 227 A, B, and C. Other questions? Yeah.
Where does the 1 minus error term come from? Number one. I get why we want to have negative error
Uh-huh.
optimization function, but why do we have specifically 1 minus error?
Well, the reason why we have a 1 here goes back to my explanation of the hard margin support vector machine last week. If you'll recall, when we do this, the hard margin support vector machine, the constraint just looks like that. The 1 on the right-hand side. And there are several reasons why that is advantageous for optimization compared to making it a 0, that some of them are subtle and hard to explain, but the one I explained last week is that it's impossible for the weight vector to W to get set to 0 when you have these constraints. Now, with the perceptron machine, we had the problem, what if W gets set to 0? Then you can't move. Here, that problem never arises because we've chosen a 1 instead. Yeah? Yeah.
But if you set C to infinity, like the offset function,
Well, I said in the limit as C goes to infinity. So, I mean, you could technically say, sure, if I set C to infinity here, you can't really minimize it. But what's happening in the limit, C approaches infinity, is essentially the slacks just have to be 0. In the limit, you have to set those slacks to 0 in order to get the best solution. I'm going to change topic now, and now I'm going to address the question of what if your data needs a nonlinear decision boundary? Does that mean you can't use linear methods like support vector machines? Well, no, it doesn't. People do this all the time. They use support vector machines to get nonlinear decision boundaries. And there's kind of a very simple and general technique for taking linear classifiers and getting them to do nonlinear decision boundaries. It's also a very general technique for taking more complicated classifiers and getting them to do even more complicated decision boundaries than they already do. So how do we do nonlinear decision boundaries with a support vector machine? Well, what we do is we add new features to our data points. Nonlinear ones. This is really easy to do. And when we take a training point and we add new features to it, essentially we think of that as lifting the point into a higher dimensional space. So essentially the idea is that we now have points in a high dimensional space. We apply a linear classifier, like a support vector machine, to those lifted points, and that induces a low dimensional nonlinear classifier for the original points that I had before I added the features. So again, I want to emphasize what a general technique features are. They work with essentially all classifiers, all regression algorithms, pretty much any machine learning algorithm that can take in data in the style of a point in multidimensional space. You can imagine processing that data to add new features. I want to build up a little geometric intuition for how this works. So let me start with what I think is pretty much the simplest, really interesting example. It's simple because we're only going to add one new feature to each training point, and test point for that matter. And this is something called the parabolic lifting map. So throughout this lecture, I'm going to use capital phi to mean the lifting function that takes one of your input sample points, training points or test points, lifts it to a point in some higher dimensional space, usually by appending some new features. In this case, I'm going to append just one new feature, and the actual function phi for the parabolic lifting map takes in a training point or a test point x and outputs the vector with one extra number added to the end of the vector, which is the length of the original vector. So again, the way you should read this is think of x as being a column vector, and so phi of x is a column vector with d plus 1 components. I've just stuck one extra number, one real number at the bottom of the vector. And so we say that this lifts x onto a paraboloid. And we can write the equation for that paraboloid by saying that the d plus 1 dimensional feature is equal to the length of the original vector x squared. Now, what makes this map interesting is that if you find a linear classifier in the higher dimensional space, the phi space, then you'll discover that it induces a sphere classifier in the original input space, or x space. So let's see visually how that works. I have, let's say, a two-dimensional set of training points, and some of them are class C, and some of them are class X. This example, well, they're not linearly separable, obviously. So what we do is we take these two-dimensional points and we map them up into three-dimensional space. They're all going to be projected up onto the surface of a paraboloid. So I will draw the paraboloid to look like this. And now here, the vertical axis is the new third coordinate that I've added to the end of every input vector. And when I map these points onto the paraboloid by making x squared be the third component, now what I'll see is that the c's tend to be in here, and the x's tend to be around here. All of these points actually lie on that green paraboloid. So now this on the right is 3D space. And so now what I'm going to do is I'm going to run a support vector machine on that 3D space on the right. And that's going to give me a linear separator. Since this is 3D space, a linear separator is going to be a plane. And now let's look at where that linear separator intersects the paraboloid. It intersects like this. So that hyperplane passes between the x's and the c's. if we take that circle and we map that circle back down to two-dimensional space, well, sorry, I should say that cross-section is technically an ellipsoid, not a circle. But when we map it down to two-dimensional space, we always get a sphere. So for instance, we might get this sphere here. In two-dimensional space, a sphere is just a circle. And so now we have a nonlinear classifier in two-dimensional space, which is a sphere or a circle. But we got it with a support vector machine, which is a linear classifier, by running the SVM in 3D on the lifted points. So that's the intuition. Now let's work out the math. So I claim that the lifted points, phi of x1 through phi of xn, are linearly separable in the high-dimensional space if and only if the original training points, x1 through xn, are separable by a hypersphere in the original X space. One little detail that I need to mention, but will mostly gloss over, is the fact that the hypersphere could have infinite radius. Now, when a sphere has infinite radius, it essentially degenerates to a plane. So, in essence, what I'm saying is that the decision boundary on the left might just happen to turn out to be a plane, like a linear separator, even in the lower dimensional space, when that's possible. Usually happen, but it can happen. So when I say that our separators in the original space are spheres, I'm not ruling out planes. The sphere could actually degenerate to a plane. Anyway, leaving aside that technical detail, let me just focus on the heart of why this is true. So let's just consider a hypersphere in the original d-dimensional space. And let's suppose its center is C, and its radius is the Greek letter rho. Then what are the points inside this sphere? Well, if a point is inside the sphere, then it has the property that if you take the distance from that point x to the center of the sphere, that's less than or equal to, well, strictly less than the radius, rho. And to make this more useful, I'm just going to square both sides. Squaring both sides is, you get an equivalent inequality, since those numbers can't be negative. And now I'm going to expand the square. So x minus c squared expands to x squared minus 2c dot x plus c squared less than or equal to rho squared. So I'm just claiming that these two inequalities are equivalent to each other. And now what I'm going to do is I'm going to take this apart into a single dot product using the lifted points. And that's going to look like this. So here's a row vector, and here's a column vector. And both these vectors have length d plus 1. So remember, C is a column vector with a length of d. So C transpose is a row vector with a length of d. And now we're adding one extra number to the end of that. Likewise, X is a column vector with a length of d. And we're adding one extra number to the end of that. And so the inequality above is equivalent to this inequality. So these are all equivalent. And it's important now to notice that this is the lifted vector, phi of x, that we're going to use to train the support vector machine. And so the way we can interpret, well, I mean, this constraint is one of the constraints we can feed into the support vector machine, for instance. And so when you come up with a solution, then this vector on the left is going to be the normal vector in the lifted space. That is Rd plus 1 in this case. And so what this equivalence says is that the point x is inside a particular sphere if and only if the lifted point, phi of x, is on one side of a particular hyperplane. Those two statements are equivalent. So if and only if. Let me just write down that conclusion. If the points are inside a certain sphere, then we can equivalently state that those points are on the same side of a hyperplane in phi space. Those two statements are equivalent. The implication works in both directions. And that is why, by using an SVM in a high-dimensional space, you can get a sphere separator in a low-dimensional space. Any questions about that? Yeah.
So the C here is also the origin of the circle or the hypersphere, and the C is also sum of the normal vector for the hyperplane we constructed.
Yeah, so the C, which is the center of the sphere or hypersphere, also becomes part of the normal vector in the higher dimensional lifted space. That's right. Mm-hmm.
Does this theorem only apply to this particular, like, V of x? Does it apply to any kind of different feature?
It only applies to this one particular kind of feature. It's meant to build your intuition so that when we go to more complicated features, you have some feeling for it. But for different problems, you will use very different features. And I'll give more examples of that in a moment. Yes? Do we have a slack parameter is what you're asking. So once you convert the d-dimensional problem into the d plus one-dimensional problem, when you put that into your black box SVM code, it will automatically do all that slack stuff for you. If you're asking how that slack is interpreted in terms of distance from the sphere, that's a little bit complicated. I would have to sit down and work out the math. I haven't done that. Sorry. Yeah? Yes. So this is just an example, one way you can add a nonlinear feature to transform your data. If you happen to know that your data is compatible with sphere separators, this is really great. If you don't, you might want to do some of the things I'm going to talk about next. Yes? Yeah, this whole idea here is that we will always have this higher dimensional space in which we can linearly separate the points. But I will add again that you can apply this technique to classifiers that themselves are not inherently linear, neural networks, and thereby take a nonlinear classifier and make it even more nonlinear, basically. So it's not just for linear classifiers, but it certainly makes linear classifiers a lot more popular. Pardon me. What I want to do next is run relatively quickly through examples of how you can do general quadratic features or even higher degree features so that you have essentially polynomial interpolation or polynomial decision boundaries. So what is an axis-aligned ellipsoid or a hyperboloid? Well, here's a few examples. Here is an axis-aligned ellipsoid. And the reason why I say it's axis-aligned is because it has several different axes. And the longest one is parallel to the x-axis, and the shortest one, in this case, is parallel to the y-axis. And likewise, here's another example. And here's an example of a hyperbola, which is also axis-aligned, again, because this axis is parallel to the x-axis, and the separator in the middle is parallel to the y-axis. All right, so if you would like to be able to generate decision boundaries with all of these shapes, then it's pretty easy to do so because in 3D, these shapes always correspond to the following formula. So we're going to fix some real numbered constants, A, B, C, D, E, F. And our bias term alpha. So I'm breaking with my usual notation my usual convention for notation by setting A, B, C, D, E, and F to be real valued scalars, because I want to roll out a bunch of Greek letters here. But assume that those 6 letters, A through F, are fixed, and alpha is fixed. And then we look at all possible solutions to x1, x2, x3 that make this formula equal to 0. That is the general formula for axis-aligned ellipsoids and hyperboloids and parabolae like these. And so, if you would like to make your SVM find decision boundaries in these shapes, then what you do is you set a phi which maps every d-dimensional point to a 2D dimensional point. And the actual value of phi for a vector x, a sample point x, is we take all of the squared terms from x1 squared to xd squared. Instead of just doing x squared, now we're doing the components of x, each squared. And do also x1 through xd, so all of the original vector is still in there. I'm going to write a transpose on that because we really want that to be a column vector. So now, when we find a hyperplane, it's going to be a hyperplane we can write in the following form. Take this row vector, dot product with phi of x, plus alpha equal to 0. That's the formula for our hyperplane separator. And this vector, you can think of it as the weight vector produced by our support vector machine. Transpose, because W is a column vector. So what we've done is we've taken in a bunch of sample points with D features each, and we've turned them into 2D features for each training point. Then we train an SVM on that, and if the points are separable by an axis-aligned ellipsoid or a hyperboloid, then the points lifted to phi space will be separable by a hyperplane whose normal vector is this. So again, in the interest of making this brief, I'm going to go straight to the more general example, which is now forget about the axis-aligned part. Let's do general ellipsoids and general hyperboloids. What do I mean by that? Well, I mean now I could have an ellipsoid like this. You can see it's tilted. It's not, the axes of that ellipsoid, the major and minor axes, are not aligned with the x and y axis anymore. And of course, hyperboloids can be the same way. Here's a hyperboloid that's not axis aligned. All right, what if I'd like to allow any ellipsoid or hyperboloid to be my decision boundary? Then, again, there is a general 3D formula for a general ellipsoid or a hyperboloid, and it's a lot like the formula I showed you for the previous example, except now you have to add all the cross terms. So there's an x1, x2 cross term, an x2, x3 cross term, an x3, x1 cross term, and then you need all the linear terms too. So now that is the general equation in three-dimensional space for any general ellipsoid or hyperboloid or conic section. And one thing I need to point out now is that when you do the lifting to add all of these different features, including the cross terms, you're not just doubling the number of features, you're now squaring the number of features. Because all those cross terms add up. There's a quadratic number of cross terms. So we can have general ellipsoids and hyperboloids for our decision boundaries, but there's a price to be paid, which is that our problem suddenly gets a lot bigger. We've squared the number of features. The amount of time it's going to take to run your SVM is probably a lot longer now. But at this point, our decision boundary can now be any general degree 2 polynomial. So there's a name for the isosurface. Any isosurface of this equation, of a general degree 2 equation, is called a quadric. So a quadric is an isosurface of a quadratic function. In the special case of 2 dimensions, it's also known as a conic section. Hopefully most of you learned about conic sections in grade school, hyperbolae and ellipsoids and parabolae. And so you can think of this as just the higher dimensional equivalent of a conic section. And so now this is a general order 2 polynomial decision function. What if we want to go to even higher degree polynomials? Well, why not? Let's look at how we would do that. I now want to allow my decision function to be any general degree p polynomial. Now, an example of that is, let's think about general cubic polynomials. And to keep this reasonable, I'm just going to do this one in two-dimensional space. So now our lifting map might be, we're going to need all of the degree 3 polynomial terms on x1 and x2. There are 4 of those 4. And then we're going to need to add all of the degree 2 polynomial terms on x1 and x2. There are 3 of those. And then we add all the linear terms. You could also, if you were doing regression, add a 1 at the end. That would be your 0 degree term. But for the support vector machine, the 1 is built in, so we don't need to add it. So now we're going from input points with d features each to now we want to run an SVM on something where every input point has d to the power of p features each. So now we're really, really blowing up the number of features. P is large especially. If you have, say, 100 features per sample point, and you want to use degree 4 decision functions, then every lifted feature vector has a length of roughly 4 million, and your learning algorithm will take approximately forever to run. But if you have really small data, you could do it. Having said that, later in this semester, we're going to learn an extremely clever trick called the kernel trick that allows us to work with these huge feature vectors very quickly without ever computing them, which is amazing. So it's called kernelization, or the kernel trick again. So even though it appears that working with degree 4 polynomials is computationally infeasible, it can actually be done relatively quickly in some cases. We'll learn that later in this semester. But right now, what I just want to do is show you what you get when you try different polynomial degrees. So here's a nice example I found online somewhere where what we have on the left is a linear kernel, meaning p equals 1. So you can see that gives you a linear decision boundary. That's your classic SVM. Now what if I use a general degree 2 polynomials instead as my decision function and plug in SVM there? Then you get that curve. And so in this figure, the decision boundary is the thick black line in the middle, and the thinner lines here show the margin. And then the last example on the far right, this is actually at degree 5 polynomials, which is pretty fancy. So you won't see that used very often in practice, but you can if you want to. And here's the decision boundary. And you'll notice it's even more sinuous than in the quadratic case. And here's the margin. And so one thing you'll notice when you do these nonlinear margins is that the width of the margin itself is not necessarily constant everywhere. You know, this margin can be wide here and narrow there. And that actually allows it to better accommodate rather complex point sets with complex decision boundaries. Yeah. Ah, so looking at, the question is looking at these three plots, do I have any indication which one might be overfitting or underfitting? I would first advise you that, as in almost always, the answer is validation is the best way to tell. Trying to eyeball it is rarely as effective as using validation as the technique to choose among these three different models. But having said that, one thing I'll notice is that these particular SVMs don't have points that are violating the margin. So that's something to take into account, is that they're all probably decent models. Then the other thing you want to look at is how sinuous is the decision boundary. If it's really so sinuous that you can't believe it's real, then maybe you shouldn't trust it. But that boundary there, that's pretty smooth. I think that looks pretty reliable to me. Mm-hmm.
How are the widths of the margins determined then, since they're not fixed? Are they just like shifted forms of?
Well, how are the widths of the margin determined? In the higher dimensional space where the points are lifted to, the margin is still the same thing. It's a linear separator. It's got linear slabs, just like we saw before. And so it's a matter of how does that map down when you project it back down to lower dimensions. And there isn't a simple answer to that. You can work through the math, but it's not simple. Yeah.
I wonder, can we see that in the right figure, the blue point on the curve have the same figure, have the same margin with the decision boundary?
Do the blue curve, sorry, does what have the same margin?
Do the blue points on the curve has the same margin with the right decision boundary?
I don't really understand your question. Can you come up after class and ask again?
Okay.
Sorry, I don't know what you're saying. Yeah. Did I get something wrong? Oh, I threw in an x3. Yeah, that's right. Well, there is no x3, of course. Is that what you're referring to, or? Yeah. Yes, this should be a 2. Sorry. Thanks. Since time is running out, let me just get to the last little section. One thing to keep in mind here is that if you raise the degree too high, eventually you will overfit the data and generalization will get worse. And so here's sort of a schematic that gives us the classic underfitting versus overfitting curve that we often find, that you will probably find that as you increase the degree of the polynomial, well, as you go from left to right, it will seem like the training accuracy is always improving, the training error is always dropping. But when you look at the test data, you'll see it drops for a while, but then as you continue to increase the degree, it probably goes up again. Because at some point, when your degree is really high, you're going to be overfitting. And really high might mean 3. By the way, this particular figure is sort of an artist's depiction. It's not actual data, but the rough idea is here, a linear decision boundary isn't flexible enough, so it underfits. But over here, a degree 5 decision boundary is too flexible, so it overfits. And the last example I want to give you of nonlinear features is, forget about polynomials. Now we're going to do something way out in left field. We're going to use an edge detector to create a new feature. What is an edge detector? They're used a lot for images. If your input is an image, like say the MNIST data that you used in homework 1, then an edge detector will look at that and try to figure out the orientation of various edges or transitions from black to white in your image. So it's essentially looking at gradients in the grayscale or in the color. And there are a wide variety of well-known edge detectors that you could use. You could hard code these and make them features as inputs to your SVM. And typical examples of famous edge detection algorithms are tap filters, Sobel filters, and oriented Gaussian derivative filters, none of which I'm going to explain, but if you want to learn more about them, there is a Wikipedia page for image derivatives that goes over a bunch of these and is a pretty good resource. And yes, you might actually want to use this for your Kaggle results in future homeworks. So a rough idea of what you can do is you can collect the line orientations in buckets, what we call histograms. So for each little patch of the image, you're going to look at it and try to figure out, for each of 12 different orientations, which orientation seems to fit most where the lines are oriented at that point in the image. And then, once you've made up those histograms, you actually input them to your support vector machine as features. And in the example I'm about to show you, the researchers did this not in addition to the raw pixels, but instead of the raw pixels. So they didn't even bother giving the pixels of the image to the algorithm. They just gave the edge detector histograms. So here's what, to give you a rough idea of what these histograms are, let's look at two images. On the left, we have a photograph. On the right, you see that we've divided that photograph into small square patches. And then within each of those patches, we're trying to figure out, are there edges with a particular orientation? So for instance, at that little patch there, it looks like we think that there's an edge oriented like that, but it might also be oriented like that. Maybe it's halfway in between, which is why both of those are lighting up. And so we'll have features that we pass in saying, oh, I think the edge is oriented this way at this particular point in the image. And by knowing that orientation, you can often get much better results on things like recognition, the MNIST challenge, than you would with pixels alone. And there's a paper that discusses this, which you're welcome to consult on while you're working on your future Kaggle submissions, if you like. It's by our own Professor Jitendra Malik here in UC Berkeley EECS, and one of his then, I'm not sure if Maggie was a student or a postdoc, but they wrote a tech report on this in 2009, which you might find really useful in your Kaggle submissions if you feel like putting in the extra effort. And what they say in their paper is that if they just use a linear SVM on the raw pixels, they got an error rate of about 15%. When they used a linear SVM on the histogram features, the error rate went down to 2.64%. That's from 15% to less than 3%. That's pretty amazing. So that's the power of nonlinear features. Any final questions? Yeah. Knowing how the model works, is there a good way to know which features to try? Oh, without knowing how the model works, I'm sorry. Not really. If you don't have any understanding of your model, then one of the most popular things to do is to have a neural network learn what the good features should be. But there are still many, many machine learning problems in which hand-coded features work really well, but those assume you have some understanding of your application. If you know your application well, like this, then hand-coded features can give you amazing advances. If you don't, then neural networks might be the best way to figure out what the features should be.